Swayam Prabha. Digital India. Educated India.
Welcome to the 6th lecture. So, in this lecture we will solve some numerical problems based on whatever was covered this week. In the first problem is based on the Euler-Bernoulli theory. It says that there is a beam and it has two piezoelectric actuators, and one is PZT5H and PZT5A. They vary by their piezo properties. Their lengths are 50.8 millimeter, width is 25.4 millimeter and thickness is 0.3175 millimeter, and they are bonded to the top and bottom of a thin aluminum cantilever beam of length L is equal to LB is equal to 1. So, this is the beam to which it is bonded. Its length is 1. Its width is 50.8 millimeter and thickness is 0.79375 millimeter. The thickness of the bond layer is 0.127 millimeter and the bond layer is assumed to be uniform. The configuration is shown below here and the material data is given. These are the material data. The 72.4 GPa has been considered to be the elastic modulus of both piezo and the beam, and D31 of the PZT5A is minus 171 multiplied by 10 to the power minus 12 meter per volt, and D31 for the PZT5H is this. So, this is our 5A at the bottom and 5H is at the top, and bond elastic modulus is given. So, there is a thin bond layer between the piezo and the beam. Properties are given. So, using the Euler-Bernoulli beam theory, we have to derive the mid plane strain and curvature, which is epsilon 0 and kappa, and plot the span wise variation of slope and vertical displacement, how the vertical displacement and slope varies along the length, and plot the span wise variation of axial displacement, the variation of axial displacement along the span wise length. And if these two patches are replaced with a PVDF, polyvinyl difluoride of same size, then calculate the new surface actuation strain and actuation bending moment for a voltage of 150 volts to the both top and bottom piezos, and the property of the PVDF is given to us. Now, we have to solve the problem. So, for the first part, now the beam is symmetric, as we can see they vary only in D31. So, that does not affect our EA, ES or EI. So, for this configuration ES is 0. EA total, if we want to find out, so there are 5 layers, 2 piezo layers, 1 bond layer in between and a beam. So, the formula that we discussed was this, and finally, that leads to this expression. And then we put the numbers. If we put the numbers, then we get this. So, we are writing the all the given properties of the piezo bond and the beam, and then finally the expression comes to be 4.103 multiplied by 10 to the power 9 Newton. So, this is our EA total. Similarly, EI total, if we want to find out, then the expression is 2 EC BC TC. So, there are 2 piezo layers and we are finding out everything with respect to the midline of the beam. So, when we find out for the bond and the piezo, we have to find out their moment of inertia with respect to their centroid, and then we shift it to our desired location, that is the midline of the beam. Now, please understand that the bond is connecting the beam and the piezo patch. So, the width of the bond and the width of the beam is same. So, that is why it is BC plus then we do it for the beam. And after we apply all the properties, then it comes to this value. Now, we have to find out the free strains in the piezo patches. So, epsilon p bottom, the free strain in the bottom piezo patch in terms of the applied voltage is D31 bottom V by Tc, and that becomes minus 171 multiplied by 10 to the power minus 12 V divided by 0.0003175, and epsilon p top. Same thing, we have to just change the D31 and then it becomes minus 274 multiplied by 10 to the power minus 12 divided by 0.0003175. Now, let us assume that the applied voltage is 150 volt. So, when the applied voltage is 150 volt, it tells us that the force Fp is, as we know, EC BC TC multiplied by epsilon P1 epsilon P2. So, in the expression of epsilon P1 and epsilon P2, we have to apply V is equal to 150 volt, and we know these quantities. So, after we do that, the value comes to be this, and similarly the expression for the bending moment becomes. So, while writing the bending moment, we have to incorporate the bond also, bond thickness. So, that is incorporated here, and the value comes to be 0.0194 Newton millimeter. So, we have found out Fp and Mp, and we have found out the properties of the sections. So, now we can write the equations and we can find out the mid plane strain and bending curvature. Now, Here ES total is 0. So, we can separately find out the mid plane strain and the bending curvature. So, to find out mid plane strain, we write EA total multiplied by epsilon 0 is equal to FP. EA total we have found out, FP we know. So, epsilon 0 comes to be FP divided by EA total, and that is equal to minus 29.91 into 10 to the power minus 6. Similarly, we can separately find out bending curvature, and for that we can solve the equation EI total multiplied by kappa is equal to MP, and from there we get EI total, and that gives the expression as this, that gives the value as this. Now, in the next part of the question, we are supposed to find out the displacement and slopes. So, we have del 2 W by del x 2 is equal to 0 when it is between the fixed end and the piezoelectric patch, and it is equal to kappa when it is between the in the zone of the piezoelectric patch, and again it is 0 when it is beyond that. So, after integrating we get the expression as this, it is 0. We have discussed it that we need to apply some boundary conditions and the continuity or compatibility conditions where the piezo ends and starts. So, after doing that we get this as the expressions, and similarly to find out W we have 0 and we have K multiplied by kappa multiplied by x 2 and we have kappa multiplied by LC square by 2 plus kappa LC multiplied by x minus x 0 minus LC. So, if you plot it, first if you plot the slope variation, it looks like this. So, this is our x 0, this part is LC. So, before the piezo zone starts, the slope is 0. In the zone of the piezo, the slope varies linearly, and after that the slope remains constant, and that slope is 1.406 multiplied by 10 to the power minus 3. If we want to plot the deformation, it would look like this. Again it is 0 at the beginning, and then there is some curvature, and after that the slope remains constant. So, there is no curvature, just a constant slope. So, this part has a bending curvature, and whatever the slope is at the end, this continues. So, this is x 0 and from here it is L c. Now, at the end of the piezo zone where the curvature ends, the displacement is 3.59 into 10 to the power minus 5 meter, and at the end of the beam, at the end of 1 meter, the displacement is 1.3 into 10 to the power minus 3 meter. So, we have found out the deflected shape. Now, we have to solve the C part of the problem, where it asks for the extension. Again, similar thing that we discussed before. So, del u 0 by del x is 0 before the start of the piezo, and then this quantity is epsilon 0 in the zone of the piezoelectric material, and then again this quantity is 0. So, we apply the boundary condition and the continuity condition and solve the problem. So, u 0 at the beginning is 0, and then u 0 in the zone of the piezoelectric material is this, and then u 0 after that is constant, which is this. Now, if we plot it, the plot looks like this. The epsilon 0 is a negative quantity here. So, the displacement is negative. So, this is a 0 line. So, this is u 0 is equal to 0 line. And the maximum axial displacement is 15.19 multiplied by 10 to the power minus 7 meter. Now, in the last part of the problem, it says that the two piezoelectric patches are replaced by a PVDF at the both top and bottom, and that makes the configuration symmetric. And if it is symmetric in terms of the piezo properties as well as geometry and the other material properties, then the MP is 0 and FP becomes 150 multiplied by and finally, FP comes to be minus 0.3048. So, there is no MP, there is only FP. So, if it can be solved as a pure extension problem in the same procedure. Now, we will look into another problem. Here again we have two piezoelectric patches at the top and bottom surface, and they are two different patches, piezoelectric PZT 5H and 5A, and their properties are given, and we have to find out the free strain variation with voltage for each piezo, and the variation of piezo strain with axial force for each piezo, and we have to find out the actuation surface force actuation surface force and bending moment for a voltage of 150 volt applied to both top and bottom piezo, and we have to find it out using the block force method as it is mentioned here, and span wise distribution of bending slope and beam displacement for this excitation. And again there is the same statement, if these two are replaced by PVDF, then we have to find out the actuation strain and actuation bending moment for a voltage of 150 volt. To solve the first problem, for PZT5H, which is at the top. So, the free strain epsilon P top is equal to D31 as we know E by, so it is D31 top E by D31 E. So, if you write it in terms of voltage, it is, we have to replace E by V by Tc, top E by V by Tc, and if we apply the properties, the value comes to be minus 0.863 V. So, for any voltage in volt, this is this, and the strain is in micro strain. And then PZT 5A, same thing, epsilon P bottom, D31 bottom V by Tc, and the value comes to be minus 538 V microstrain. Now, we have to find out the relation between the strain and the force. So, for that we can use the constitutive relation in this form. Now, here this epsilon 1 and sigma 1 denotes the strain in direction 1. So, they and the stress in direction 1. So, they are not for piezo 1 or piezo 2. So, if we from this equation we can just get the relation minus 86.3 plus F top divided by 0.584, and this gives us in microstrain, and the force F top comes to be 0.584 strain, I mean strain, let us see, call it, this is not, this is just epsilon top, we cannot use P because it is not a free strain. So, F E plus 50.4. Now, we this we just got by putting the values here. We know Tc, we know D31, and S11E, it is just 1 by EC, and from there we can get the relation. So, from here if we put epsilon top is equal to 0, that gives us the block force F BL top as 50.4 Newton, and if we put F top is equal to 0, that gives us the free strain epsilon P top is equal to 80 minus 86.3 microstrain. Now, in all this analysis, the value of V that has been assumed as 100 volt in all this analysis, and even whatever is going to proceed now for the bottom piezo also. Now, the similar quantities can be found out for the bottom piezos. So, F bottom can be written as 0.584 epsilon bottom plus 31.42 and from here we can find out the F block force at the bottom as 31.42 Newton and free strain at the bottom as minus 53.8 microstrain, and again 100 volt of voltage is assumed here. Now we have to find out the actuation forces to proceed further. So, we know we already discussed that this is a case of asymmetric actuation where D31 are different for the top and bottom pieces, and we saw that the relation comes in terms of alphas and the free strains. So, we have to calculate the alphas, and alpha 1 is EAC 1, where it is EAC 1 is EAC of one of the piezo patches, and EAC 1 plus 4 by EAB. Alpha 2 is minus 2 into AB, and using these alphas we can find the actuation extensional actuation force as alpha 1 plus alpha 2 sigma p top epsilon p top plus epsilon p bottom, and that comes to be minus 43.82 Newton, and the moment comes as TB by alpha 1 minus alpha 2 epsilon p bottom minus epsilon p top, and the value comes as 5.13 into 10 to the power minus 3 Newton meter. Next is we have to find out the a deflected slope, a deflected shape. So, the governing differential equation is this, is equal to m by EIB, where m is 0 when x is less than x 0, and when m is 5.13 multiplied by 10 to the power minus 3, when x is between x 0 and LC, and m is 0 when x is beyond LC plus x 0. And again if we apply the boundary conditions and the continuity at the beginning and end of the piezo, we get these relations, that del W by del X is equal to 0 and W is equal to 0 in the first zone, and then we have del W by del X, which is slope, is equal to 0.0335 x minus x 0, and W is equal to 0.0167 x minus x 0 square when we have LC, and then we have, and in the last region we have del W by del X is equal to some constant, and that is in radian, and W is equal to 4.31 into 10 to the power minus 5 plus 1.7 into 10 to the power minus 3 x minus 0.1016, and these values will come in meter. So, these are all in radian and this in meter. So, again if we plot the slope distribution, it would look like this, and if we plot the displacement, it would look like this. So, this is our x 0 and this is LC. Similarly, this is x 0 and this is LC. Now, the last part of the problem says that we have replaced the piezo patches by 2 PVDFs. Now, for PVDF, the free strain is this, and that gives us minus 0.063 volt, and this is micro strain. So, V is equal to 150 volt, that gives us epsilon P is equal to minus 9.5 micro strain. Now, again it is a symmetric case because the properties are symmetric. So, there will be no bending actuation. So, M would be 0. So, bending actuation would be 0. So, there will be only extensional case, and that also says that kappa is 0, and it is only a pure extensional actuation, and for that we get epsilon P based on the expressions that we derived before. For a pure extensional case, the mid plane strain comes to be minus 0.104 micro strain. Now, just one point to remember, in this analysis the voltage as stated in the question was taken to be 150 volt. So, with that I would like to conclude this lecture. Thank you very much.